Namaste and welcome to this lecture on mathematical foundations for machine learning, and we have been looking at the area of orthogonality, projections and so on, and in the last lecture we figured out that the best approximate for a vector in a vector subspace is basically the orthogonal projection of that vector into that onto that subspace. And we said that towards the end of the lecture we said we will start with the real symmetric matrices. So, let us start with real symmetric matrices this lecture and look at the properties of real symmetric matrices. Real symmetric matrices, right. So, what are these? I mean, what do we mean by real symmetric matrix? We say that a matrix is real symmetric. A matrix A is real symmetric if say if all its elements are real and A transpose is equal to A. This is when you call a matrix to be a real symmetric matrix. What does it mean? It says that the matrix must be symmetric. So, example, recall that we have been working on this matrix for quite some time, 2 1 1 2. This is a real symmetric matrix where all the elements are real and the transpose of this matrix is nothing but the what would you call the matrix itself. The transpose of this matrix is basically matrix itself. And remember, we have always associated a matrix with a linear transformation. So, let us also try to look at it from the perspective of a linear transformation. So, what we are going to do is we are going to look at a linear mapping, right. So, we are going to say that let T be a linear mapping such that T maps a vector in the vector space V back to the vector space V itself. So, T maps V to V, let T be a linear map such that this happens. So, T is said to be a symmetric matrix or symmetric transformation said to be a symmetric transformation or let us say T is said to be symmetric if it is basically this. You must have the inner product to be defined in the subspace. So, what we are going to do is we are going to say that if the dot product of the transformation on a vector u with a vector v is the same as the dot product of the vector u with the transformation of the vector the transformation on the vector v, right. So, that means we are going to say that, let us make this clear, we are going to say that the vector space V is an inner product subspace or inner product vector space, inner product vector space, and U and V are elements of this big V, right. U and V are elements of this big V vector space, right. Okay. So, if this happens, that is the dot product of the transformation of u with the vector v is the same as the dot product of vector u with the transformation, the vector that you get after transforming the vector v. This is basically what you call as a symmetric transformation, right. Okay. Now, what we want to do is let us look at it this way. So, let A be a real symmetric matrix associated with the transformation T. matrix associated with T. Say for example, what we are going to do is we are going to say that T is such that T basically maps, let us say, Rn to Rn. That means it maps an n component vector to another n component vector true, where we say T of u is basically given by AU. This is what we have. T of u is basically AU. So, what is the thing that we are going to say? We say that T is symmetric T, if you have A to be the symmetric matrix associated with this transformation T, then T will be called as a T is basically a symmetric transformation that you have. So, what we are going to say is, suppose we consider let us say U and V be elements of Rn, then what I am going to do is let me look at the transformation, what the transformation does to U dot product with this vector V. The transformation of U is basically captured as AU. So, I am going to have AU dot V, which is nothing but, I can write this as AU whole transpose into V, because we know that U dot V is nothing but U transpose V or V transpose U. This I am going to write this as U transpose A transpose V. This is what we have, and since A is symmetric, and real, we have T of u dot V is equal to U transpose A V, because A transpose is same as A, which is nothing but U dot A V, which is nothing but U dot transformation of V, right. We have this. Okay. Now, there are quite a few things that we are going to look at here. The first and foremost important property of real symmetric matrix, right. So, we are going to write that. So, the first and foremost important property. So, let us look at this properties of real symmetric matrices. The first property is very interesting. The eigenvalues of a real symmetric matrix are always real. Remember, we did this, recall. We had this rotation in 2D, let us say by 90 degrees counterclockwise direction. We had the following, with the matrix was A, which was given by 0, 1, minus 1, 0, and for this we figured out that the characteristic polynomial was the characteristic polynomial here lambda squared plus 1 is equal to 0, or the characteristic equation in this case, the characteristic equation is basically lambda squared plus 1 is equal to 0, which implies lambda is equal to plus or minus I. this is interesting because here we had a real matrix. The real matrix ended up having complex eigenvalues, and the complex eigenvalue here you typically see that they appear in complex conjugate pairs. Now this kind of a situation we will never land in if the matrix is real symmetric. So you can ask, so what, I mean, on what basis do you say this? Do we have a proof for this? Can we prove that the eigenvalues of real symmetric matrix are always real? Yes, of course. Let us look at a quick proof of this, and then we go ahead, right. So consider, okay, A to be a real symmetric matrix, a real symmetric matrix. I will use this RSM to indicate that it is a real symmetric matrix from now on. So I will do RSM this way, right. I will write this. So what are we going to do is, okay, we have the characteristic polynomial, assume that, okay, we have a complex eigenvalue. So let lambda be complex root of A, complex eigenvalue of A. Therefore, we know that the complex conjugate lambda bar is also an eigenvalue of A. So therefore, lambda bar, which is the complex conjugate of lambda, is also an eigenvalue of A. Right, this is what we have. So let us assume that, okay, let U be an eigenvector associated with lambda. This could be a complex eigenvector. So let U be an eigenvector let us say possibly complex, right. So we can actually say, okay, anyway, okay, we will put this, let U be an eigenvector associated with lambda, because we have already taken lambda to be the complex eigenvalue. So we will say associated with lambda. Then what is it that we know? We know that A u is equal to lambda u. This is something we know, right. A u is equal to lambda u, because that is the non-zero eigenvector that we are looking at. So A u is equal to lambda u. So now what I want to do is, I want to look at the length of this vector, lambda squared length of this vector, which is lambda u the whole squared, the squared norm. This is going to be lambda u dot u bar. Let me take this as lambda u dot u star or u bar, whatever, okay, u star, where I will take u star to be the complex conjugate eigenvector. Complex conjugate, right. Now I can write this lambda u dot u star as basically a u dot u star, right, because we assume that it could be a possible complex eigen, because your eigenvalue is complex, we say that, okay, you could have this. Now what do we get here? We basically have a u the whole transpose into u star, which is nothing but u transpose into a transpose u star. This is what we have, right. This is basically u transpose a transpose u star. This is what we have, and we have u transpose into a transpose u star. But remember, which is basically, okay, I can write it this way. This is nothing but u transpose A transpose is same as this A, so I will write this as A, and then I will write this as U star, right. A transpose is A because A is real symmetric matrix, for that we are considering. So, A transpose is equal to A using A transpose is equal to A. We have U transpose A U star. Now, I can write this as okay, fine, okay, let me do this. So, A U star, I can write this as okay, complex conjugate of this lambda. So, I will write this as lambda bar, and then I will take this as U star, which is nothing but U transpose. I will take this as lambda U, the whole bar, that means it is a complex conjugate. So, you just take it this way, right. So, what we have? We have U transpose into, let us say, lambda bar U star is what we have, which is nothing but lambda bar into U transpose U star. Suppose if U and U star are complex conjugate pair, so I have basically I will take this as lambda conjugate here, lambda conjugate into U transpose U star. U transpose U star is nothing but, so we have lambda star into lambda conjugate into the same thing, the vector length of U. So, what do we have here? We have lambda squared length of U is the same as lambda bar into the squared length of U, which means I am going to have lambda minus lambda bar into this is going to be 0. Now, what does this mean? The vector U is a non-zero vector, therefore, lambda must be equal to lambda conjugate, right, lambda must be equal to the lambda conjugate, and that will happen only when lambda is real, right. This implies lambda is real, right. So, whenever you have a real symmetric matrix, this is very interesting, the eigenvalues are always real, right. Now, does it stop here? No, there are plethora of properties. The second property that we are going to look at is basically this. Let us look at this. The eigenvectors corresponding to distinct eigenvalues the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix A are always orthogonal to each other. This is very interesting. The eigenvectors corresponding to distinct eigenvalues of real symmetric matrix A are always orthogonal to each other. That means we have already seen that the eigenvectors can be used as basis for the column space of A. Here we see that the eigenvectors being orthogonal, all you need to do is just make them unit vectors by dividing by the length of the corresponding eigenvector. We end up getting orthonormal basis for the column space of A using the eigenvectors. So, that is pretty interesting, right. So, this is very interesting, and we will see that this fact is what is exploited in your principal component analysis of the covariance matrix. When you do, you will use this fact. So, let us look at this. So, can we again prove this? Yes, of course, you have a very interesting small proof. Let us look at that. Suppose just take distinct eigenvalues. Suppose I take this, let us say T is a mapping from say V to V, and A is a real symmetric matrix matrix such that let us say T of any vector u is equal to a u. So, what I am going to do is I am going to have this. So, let me take this, make this x, so that it will be easy for me. So, I will take this as T of x is equal to a x for x in v. So, let u and v be the eigenvectors associated with distinct with eigenvalues, let us say lambda and mu, eigenvalues lambda and mu of a, right. We will take this lambda and mu, the eigenvalues of the matrix A. Now, what we want to prove? We want to prove that, so claim u is orthogonal to V, right. Claim is u is orthogonal to V when lambda and mu are distinct, when lambda is not equal to mu. So, let us say lambda and mu of A, that means lambda is not equal to mu, we are already taking that, they are distinct eigenvalues. Okay. So, let me make this associated with distinct eigenvalues lambda and mu of A. So, what do we have? We have this. Since okay, let us do this. Since u and v are eigenvectors of T, we have T of u is equal to lambda u and T of v is equal to mu v, right. We have this. So, let us take this, the dot product of, okay, so let us do this. What is lambda u dot v? Lambda u dot v is nothing but, I can take this as, okay, lambda times u dot v is nothing but, I can take this as, let us say lambda u dot v, which is nothing but a u dot v, which is nothing but u transpose A transpose into V, which is nothing but u transpose into A V, which is nothing but u transpose into mu V, right. We have this, right, which I can write this as mu times u transpose V, which is nothing but mu times u dot V. Now, what do we see? We see that lambda times u dot V is equal to mu times u dot V, which implies lambda minus mu times u dot V is equal to 0, which implies, see in this case lambda is not equal to mu, we already know that, we know that lambda is not equal to mu, we know that lambda is not equal to mu, therefore, the only possibility is u dot v is equal to 0, which implies the eigenvectors corresponding to distinct eigenvalues corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal. Not surprising, we have already seen an example for this. We took A to be 2 1 1 2 and we had lambda to be equal to 3 and the corresponding eigenvectors was 1 1 and we had mu is equal to 1 and the corresponding eigenvector was 1 minus 1. Now lambda is not equal to mu, therefore you say this is basically u dot v, you just check this, take this as u and take this as v, you have 1 1 dot 1 minus 1 which is 0. We have already seen this just now. We could, when we put these things together, we realized that yes, when you had the matrix A which was real symmetric, this matrix 2 1 1 2, the eigenvalues were distinct and then the eigenvectors are therefore orthogonal to each other, right. In fact, one more interesting place where we can see, suppose I take this matrix A which is 1 0 0 0, this is basically a matrix which projects every vector in R2 to onto 1 0, the direction 1 0, right, it is going to project it onto the x axis or x1 axis. So we have this, in this case lambda is equal to 1 and mu is equal to 0. Pretty interesting here. What are we going to see? Any vector along the x1 axis is going to be along the x1 axis. That means we have 1 0 0 0 into, what do we have, 1 0 is going to be 1 0 itself. That means the eigenvector 1 0 is associated with the eigenvalue lambda is equal to 1 for this projection matrix and it is a symmetric matrix, right. A transpose is equal to A. Projection matrices are always symmetric. Now what about the other eigenvalue? We have mu is equal to 0, mu is equal to 0 corresponding to this. Suppose I take this 1 0 0 0 and then I take 0 1, what do I get? If I take 0 1, what is the eigenvalue that I get? So basically I am going to get 0 0, right. Okay, let us do this. Right, any vector on the okay, let us look at this. Any vector, we will try to understand this a bit better. So any vector on the y axis is going to get now projected to the 0 vector, right. When you have this corresponding to mu, any vector that you have on the y axis is going to project, it is going to get projected onto the this one. Right. So let us basically solve the system of equation and see what we get. Okay, what is the system of equations? We have x1 plus 0 x2 is equal to 0, which implies x1 is equal to 0, x2 can take any value, let me take k. So I can write this as 0 times 0 1. So we see that again these two guys are orthogonal to each other because we are looking for non-zero eigenvectors. So this is what we see here. So whenever you have distinct eigenvalues correspond of a real symmetric matrix, the eigenvectors are orthogonal to each other. Even more interesting, this, what do we have, real symmetric matrix, the property number 3 that we are going to write now. Any real symmetric matrix or every real symmetric matrix is orthogonally diagonalizable. Every real symmetric matrix is orthogonally diagonalizable. Now what do we mean by this orthogonally diagonalizable? This means, you recall, we had this, recall A is equal to P inverse, right, and D is equal to P inverse AP. This is what we had. Now if the matrix A is real symmetric, if A is real symmetric, then we know something. What is that? The eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Therefore we already saw that the orthogonal matrix will always have inverse to be equal to transpose. Then we say that D is equal to Q transpose AQ, right. We have Q transpose AQ, which gives me diagonal, this one, diagonal matrix, where Q basically contains orthogonal eigenvectors. You can normalize them and then make them unit vectors, and you can do this, orthogonal eigenvectors of A. Is this clear? Now in fact it is here that something interesting that comes up into picture. Let us see what that is. Let us just take a quick look at this orthogonal diagonalizability, where we had D is equal to Q transpose AQ, or A is equal to, we had Q D Q transpose in line with our PDP inverse, right. Now what are we going to do? I want to look at the, suppose, I mean we already know that if, okay, this is A is a real symmetric matrix with distinct eigenvalues. Distinct eigenvalues. Now what are we going to do? I want to study, suppose I say that the matrix A is basically associated with a linear transformation or linear map T, symmetric matrix. So we have associated with a linear map T which is symmetric. Right, because A, we always say A is here a real symmetric matrix. So we say that A is basically the matrix associated with the map T. Therefore since A is real symmetric, you say that T is also symmetric. Now I want to look at, suppose I say this, let us look at this, consider, let us say X in R2, basically I am going to say this, T maps R2 to R2, okay, and T of U is equal to, let us say, lambda U, and T of V is equal to mu V, and therefore this implies AU is equal to lambda U and AV is equal to mu V, is what we have, right. Now what am I going to do? I want to find out, suppose if X is a vector in R2, if X is an element of R2, suppose I have X to be a vector in R2, I want to find out what is this transformation doing to this vector X, right. I know what the transformation does to the eigenvectors, basically the vector U and vector V, it just scales, but for any other vector it need not. For example, I have this matrix 2 1 1 2, when the vector is basically 1 1, it just scales the vector 3 3. When the vector is 1 minus 1, it basically scales the vector which is 1 minus 1, right. You put this matrix here. Suppose if I give this to 1 0, I do not even know what is this matrix doing except the fact that I get to 1. When I try to transform this vector 0 1, I end up getting the vector 1 2, I do not even know what is happening. So I want to study what is the effect of T, what is the effect of this transformation T on the vector X, for which I am just going to take T to be a linear map operating on R2. So you get back another vector in R2, and we have U and V to be the orthogonal eigenvectors of the real symmetric matrix A, assuming that T is a symmetric transformation, and lambda and mu are the distinct eigenvalues. So this is what we have. So I want to study what is Tx, what is the effect of transformation T on X. Now how do we study that? So we know it very clearly. What is that? We have T of x can be captured as matrix operation as Ax. But recall that A can be written as Q D Q transpose, therefore where Q contains the eigenvectors, right. It is basically like what we had here. So Q is an basically Q contains the orthogonal eigenvectors. This is what we have. I can normalize these eigenvectors and then make the length 1, so it is not a problem. So I have A is equal to Q D Q transpose. So let us write this again. A is equal to, I have Q, which is basically the eigenvector u and the eigenvector v, and I have lambda 0 0 mu, and then what do I have? I have this, which is basically u transpose and v transpose, right. This is what I have. Now I want to study what is Ax. T of x, the transformation on the vector x is captured by Ax, and A is basically this matrix, this product that we have, which is u v into lambda 0 0 mu into u transpose v transpose, and we have x, right. And what is interesting, I will write this, u dot u is equal to 1, v dot v is equal to 1, u dot v is equal to v dot u is equal to 0. That means this corresponds to unit length vectors and this corresponds to orthogonal vectors, therefore I am going to say u and v are orthonormal vectors, right. So what do I have here? I have T of x. T of x is basically this following, which is nothing but, let us write this again, u v and lambda 0 0 mu and what do we have here? T of x is basically Ax, which is equal to this. So I had u transpose into x and v transpose into x. So I will take this as u transpose x, v transpose x, right. That is easy to do, u transpose x and v transpose x. So what do we have here? We have here u v, then I have lambda u transpose x mu v transpose x. So this is what we have. I can multiply this, I get this. So now what we have? I have u into lambda u transpose x plus v mu v transpose x. This is basically Ax, and which is basically the effect of the transformation T on x, where T is symmetric. Now this guy is a scalar, this guy is a scalar, so I will pull them out. I will say this is going to be lambda u transpose x plus mu v transpose x. Now this is something interesting, we have done this before. What is that? This I can write this as, okay, u transpose u, anyway the length is 1, this I can write this as v transpose v. So what do we get here? We basically get this as lambda into u transpose divided by u transpose u x plus mu into v transpose divided by v transpose v into x. Oh, this is something which we already know. What is that? This is basically a matrix that projects along u, and what about this? This matrix projects along v. And what can we say about u and v? U and v are basically orthogonal vectors or orthonormal vectors, unit vectors which are orthogonal to each other. Therefore the effect of the transformation T on any vector x, where T is a linear map which is symmetric, which is basically associated with this matrix A, which is A, I will take this as real symmetric matrix x, real symmetric matrix again, is basically given by lambda u transpose x plus mu v transpose x. That means the effect of this transformation x, I mean the effect of this transformation T on x is basically to project this x onto two orthogonal directions, namely the orthogonal directions corresponding to the orthogonal vectors, eigenvectors, and scale those projections by lambda and mu. So the effect is nothing but projecting X onto orthogonal eigendirections or orthogonal directions and scaling the projection. Right. In fact, from here we can see one more thing. What is that? A is basically lambda u transpose plus mu v transpose, and here A is going to be a 2 by 2 matrix because I have taken A to be acting on 2 component vector. That means the transformation, the map T is going to act on 2 component vectors. So I am going to take this as this, and therefore u transpose, this is going to be a 2 by 2 matrix of rank 1, v transpose is going to be a 2 by 2 matrix of rank 1, right. This is also going to be 2 by 2 matrix of rank 1. Now what are we going to say? We are going to say that I can write A as a linear combination of rank 1 matrices of dimension 2, right. Therefore this eigen decomposition, this is basically eigen decomposition in the sum form. Now what is interesting is the matrix U transpose and the matrix V transpose are linearly independent matrices, and therefore in the vector space of matrices these two will be bases. In the vector space of, let us say, real symmetric matrices, these two u transpose and v transpose in turn will become the basis, and if you change the value of lambda and mu you get a different value of A. That means A is basically written as a linear combination of the basis vectors here. So what have we done? We have written an n by n, I will generalize this, an n by n real symmetric matrix is decomposed into sum of n rank 1 n by n matrix, right. These are some of the most important and beautiful properties. Of course there is one more that is coming up, but what we will do is we will just wait for that for a little bit more of time when we do the idea of calculus, when we want to do this optimization of multivariable optimization. I will revisit this real symmetric matrix again from a completely different perspective, and we will see how this real symmetric matrix idea keep coming, and they are very, very significant in many of the topics that we deal with in machine learning, right. So what have we done in this entire module? This week we basically looked at the idea of orthogonality. We looked at orthogonality basically by introducing the idea of inner product. We looked at the inner product of the dot product of the matrix, of the two vectors, and then we said that look, if the dot product of the two vectors is, let us say 0, then the two vectors were orthogonal to each other. This is something which we did, and in addition we also looked at the projection of a vector along another direction, and we said that orthonormal bases were easy to handle with because you can get any vector in terms of an orthonormal expansion. Orthonormal basis expansion is something which we could get, and that is where we saw Fourier expansion. And if you are given linearly independent vectors, you could always orthogonalize them using Gram-Schmidt procedure by taking one reference vector, then taking the second vector, projecting onto this reference vector and subtracting the projection. In fact, Gram-Schmidt orthonormalization process is actually another test for linear independence. If suppose the vectors are not linearly independent, you will end up getting a 0 vector in between, and you will see that okay, the vectors are not linearly independent. So you have that idea also in the Gram-Schmidt orthonormalization process. So given a set of vectors, linearly independent vectors, you could always generate orthonormal vectors. And then we said that you could look at orthogonal complement vector spaces or subspaces of a orthogonal complement of subspace, and we said that okay, we could map it to the column space of the matrix A and the column space of A transpose. and then we said the null space of A and the column space of A transpose are orthogonal complements of each other, and so are the column space and the null space of A transpose. So we said all these things, and then we looked at projections, the idea of projection being, the projection matrix being symmetric and idempotent. And then we looked at various other things. We also said that we could actually, given a vector, we can find a best approximate of that vector in any vector space, and we figured out that the best approximate is going to be the orthogonal projection, which is going to give you least error in squared sense. And then we moved on to the idea of real symmetric matrices, which are going to play a very key role in machine learning. So we said that real symmetric matrices have some beautiful properties, of which we looked at 3 of them. One is basically saying that the eigenvalues of real symmetric matrices are always real. Then the eigenvectors corresponding to the distinct eigenvalues of real symmetric matrices are orthogonal to each other. And then we said that real symmetric matrices are always orthogonally diagonalizable. The one property which I have not done now, I would probably look at, recap this when I go there to optimization, is the idea of definiteness of a matrix: positive, definite, positive, semi-definite, negative, definite, and negative, semi-definite, indefinite. These things I will again visit when I do optimization, where we will be talking about Hessian matrix and so on. And with that note, we wind up the foundations of linear algebra ideas. In the next class, we will be looking at singular value decomposition and principal component analysis with applications. That will be done by Dr. Ashok Rao. Thank you. Namaste.